First time I've done one of these. This is a exponential floor equation. And by that, I mean the exponent here that I'm applying to this base of 3 is actually the floor function. And it's the floor function for 1 over x. Now, I tried to do this just sort of by hand. And I got to realize I was doing a lot of calculations. It turns out that this lemma right here is super, super useful. And I noticed this pattern, and it's, I mean, I spent an hour on this before I realized this lemma is the way to go. But you guys know the floor function always maps to an integer. Now, for this problem, we're dealing with positive numbers. So the floor function always maps to a natural number. It can map to 0 also, and we're going to deal with that actually. But notice the relationship here. K is a member of a natural number if and only if x is in this interval 1 over k plus 1, comma 1 over k. Now that makes a little bit of sense because you're taking reciprocals, right? So it's very clear that if k, 1 over k better be in the set, because if you put 1 over k right here, 1 over k is k, right? So that's easy enough to see. Now the 1 over x function is a decreasing function. And so you can't put 1 over k plus 1 into here because that would be 1 over k plus 1, which is k plus 1. And we're just interested in we're talking about k here. All right, we're talking about k, not k plus 1. So you have to have the open and close setup right here. Now, that's a lot of talking, but let's take a look at a concrete example here. What if you let k equals to 3 and you trust this lemma that I've written down for you, okay? So we're going to write down the floor of 1 over x is equal to 3. If and only if x is contained in this interval 1 over k plus 1, which is 1/4 in this case and 1/3. Now, just to trust a little bit better, notice that 1 over 4 is the same as 6 over 24. 1 over 3 is the same as 8 over 24. 8 plus 6 is 14. So you get 14 over 24, but that reduces to 7 over 27, right? So this is kind of a check that you would believe this result. And you can check it with various numbers, but using this result really makes life a lot easier because I was trying to do the calculations each time. It was just getting very oppressive. Now, so what makes this one easier than it looks is that no matter how complicated this piece is right here, this could be anything. It could be a three-term expression. The floor function is always going to return a natural number, and it can return 0. And I'm going to talk about that case. So in other words, you're just going to be setting the equation equal to 3 raised to various powers. So that's nice. That's nice. Even though this looks messy, the floor function is very strict. It maps to natural numbers or whole numbers in this case. Now, so what I did here, and you can notice the pattern. This is kind of a sneaky one right here because you see 3 to the 0. If you're going to do a floor level of 0 right here, that would correspond to, you see right here how we have 3 to the 0. Well, that would mean this right here. For this to have a floor of 0, it would have to be in the interval 0 to 1. Now I know that looks crazy, but like for example, pick 7/8, right? 1 over 7/8 is 8/7, and it has a floor greater than or equal to 1. All right. So in other words, if you're in this interval, and this is very believable, that all the fractions less than 1, greater than 0, their reciprocals are going to be bigger than 1, right? So now, and that's exactly what I did right here. If you'll notice the pattern here, 3 to the 0 is 1. Okay, 3 raised to the 0 power is the 1 that you see right here. I'm just solving this. And notice when we actually do that, we get minus 91 over 12. Well, that certainly can't be a number between 0 and 1, right? So minus 91 over 12 is not a solution, all right? Simply because it would violate this condition on the floor function. Now, so let's try the next one, 3 to the first. And hopefully that was probably a little confusing, but maybe you'll see the pattern once we go to this next screen. Okay, now if you take a look right here, just take a look at the pattern that we have here. It's 1, 2, and 3 for the exponents right here. We'll notice that you have 1, 2, and 3 for the floors, and that wasn't real obvious on the last one. You see 3, 2, and 1 right here, and that's exactly corresponds to these exponents, all right, which you would be setting the floor equal to. All right, and let me back up. See, this does say 3 to the floor of 1 over x, all right? But still, those exponents have to be equal to 0, 1, 2, and 3, and so on. Okay, so that's what's going on here. Now, so let's come back. All right, so again, if you run through the arithmetic here, you would get this negative value, but 1 over x using that result from a while ago, y'all, I'm sorry I'm having to switch screen, but if the floor is equal to 1, okay, this result right here says the interval would be 1/2 and 1, right? And so that's what we have on this next screen. I apologize, I should have written this on the next screen. But again, we have this negative value. That's why I made it red. It can't be contained in this interval. Okay, so next we're off to checking the floor value of 2 here. You see we have the exponent of 2. We have the exponent of 2 right here. Now notice we get something that clicks here. If you do the arithmetic right here, again, 9 minus this number happens to be this number right here. Now, notice it's not hard to verify that 5 over 12 is contained in this set. Okay, 5 over 12 is contained in this set because this would be what, 6 over 12 plus 2 over 12. Or wait a minute, this is 4 over 12 plus 6 over 12 is 10 over 12, right? And so this would be contained in that set. 5 over 12 is definitely contained in this set, right? Because this piece right here is 4 over 12, right? So 5 over 12 is definitely right in the middle of this set. Now, I could say, all right, we know that the functions are increasing, the linear function's increasing, the 1 over x function is decreasing, so I could say stop right now. But I just wanted to go through one more example here. I tried it for the next level floor of 3 cubed. You can see 3 cubed is the 27 you see right here. This 3 right here, this 3 exponent right there, that exponent of 3 is exactly this 3 right here. You see, you get this positive number here, 221 over 12, but it's certainly way off. It's not contained in this set, okay? Now, I know that was a little confusing, but I really couldn't think of a better way to organize this. So what we know is that the only solution to the equation is 5 over 12, okay? The only solution is 5 over 12. And just one last thing I'd like to say, you may say, well, why can't you just keep checking? Well, you could, but you see, there's a kind of a terminate condition here. Notice that this equation right here is just an increasing line, right? X plus this number 103 over 12. It's just a line of slope 1 that's always increasing, right? So this is no floor going on here. This is just an increasing function. But notice that this 1 over x function that's right here, that 1 over x function is definitely a decreasing function. If you think of the graph from 0 to infinity, it decreases. It decreases. So if it decreases, its floors decrease also. So you see, once they pass each other, there's no way that they can agree again. They just happen to pass each other in the night there. And so again, only one solution, folks. Only one solution to the equation is 5 over 12. And please comment if you can think of a better way to present it. I thought about how to present it for a really, really long time, and this is all I can come up with. So again, I hope you enjoyed it.